let's do one more thing on our, before we move on, let's do one more thing on the particle in free space, or the free electron uh, application of Schrodinger's equation. So last time what we're going to do this time, we're going to apply boundary conditions. So last time we found that our little psi of x, had this form: a e to the j square root of me over h bar x. So we had our wave number k, and then we have b e to the negative j kx, like we said last time. Well, now let's apply boundary conditions. By the way, as we said last time, this represents a traveling wave. In fact, this part is going to give us a positive x traveling wave. This is going to give us a negative x traveling wave, because the time dependence, because it's e to the negative j omega t. Okay, so we've got traveling wave. We've got also think of this as a plane wave. We talked about plane waves last semester in electromagnetics. Here we have plane wave. Again, last time we also saw some relationships between an energy and momentum, energy and wave number, wavelength, and that was all good. Well, boundary conditions. Our first one, just to remind ourselves what we have, is the integral over all space of psi star psi is equal to 1. That's our normalization boundary condition. And we also have the wave function has to be finite, single valued, and continuous. And its derivative also. So here we've got, with respect to x, the derivative is also finite, single valued, and continuous. And just by looking at the form of this, our second and third boundary conditions are automatically fulfilled. Psi of x is finite, single valued, and continuous, and so is its first derivative. So we're all fine. The potential energy function is finite everywhere. It's 0 in this case. So these are satisfied. 2 and 3 are satisfied. So you need to think about the normalization. That's the only thing left to do. What about normalization? Well, we need to use some physical insight here to figure out how to proceed and see what this is going to look like. We have a free particle, and let's assume that it has a source and that it's coming from somewhere. There's obviously a source because it exists, and let's assume that it's the source of the particle is to the left somewhere. It's over here to our left somewhere. So the particle is traveling to the right. So and because the potential energy is 0, the potential energy function is 0 everywhere, there's no way for it to bounce, to be reflected. There's no barrier. So what we have, because the source is somewhere to the left, the electron or the particle is then coming our way, moving to the right in the positive x direction, and there's no way for it to be reflected and have a negative x traveling component. What we have is a positive x traveling wave. That's all we have. So what we had before was our complete solution in case there was some reflection. Here we have no reflection. So in terms of our coefficients that we had, A for our positive x traveling wave is not 0. For our negative x traveling wave, B, that coefficient, that scaling factor is 0 because we have no negative x traveling wave. So we're going to have to find what A is. We figured out from using our intuition that B is 0, but now we're going to have to figure out a value for A. Well, in one dimension, in 1D, our integral over all space amounts to integrating from negative infinity to infinity in x. And that integral is equal to 1 for normalization. Now, we have to use some more intuition. This gets a little weird, making a series of assumptions here. One assumption that we said is that the source of the particle is to our left, so the particle is moving to the right. We also used our intuition to know that it's not going to be reflected, so there's no negative x traveling wave, it's just a positive x traveling wave. But now we're going to say that this particle is in a large box. Maybe that box is the universe. Maybe it's a crystal, semiconductor crystal, or whatever the case. It does have some boundary actually. So we're not actually going to go all the way from negative infinity to positive infinity. There's some large box that this wave is in. So we have a large one-dimensional box of size L. So L is the dimension of our box. And we have our wave function, just to summarize what we've got here. It's going to be A e to the I kx minus omega t inside the box, and it's going to be 0 outside the box. So it does have some constraints, but they're way out there. This is a box that is large on the microscopic scale. And so this would mean, for instance, that L is much, much greater than about 100 angstroms, or about 10 to the minus 8 meters. That would be sufficiently large. On our scale, macroscopic scale, that's big. That's tiny already, but for the electron, that's pretty small. I mean, that's big enough. That's big for the electron. So the electron is not complete, or the particle is not completely free to roam in infinitely large space. All right. So now we can apply our normalization, and we're going to integrate over the box, over the size of the box, because outside the box our function, our wave function actually is 0. So now we have the integral over the box of length L, and we have the magnitude squared of A e to the I kx minus omega t squared dx. This is equal to 1, but the magnitude here of our varying part, that's complex exponential, that's magnitude of 1. So we have the integral over the box of length L, magnitude of A squared dx is equal to 1, because again the magnitude of the complex exponential is equal to 1. And this gives us the magnitude of A squared times L is equal to 1, and the magnitude of A is equal to 1 over the square root of L. Now we can just take, we don't really care about the sign or the phase. A could be complex, have a non-zero angle, but we can just drop that and say A is positive. That would introduce a phase shift. We don't really care about that. So A is 1 over the square root of L. So we're letting A be real and positive. That's fine. All right, so that would mean that our scaling factor is pretty small. The bigger the box, the smaller A is, but we have applied our normalization condition, and because the particle is in fact actually constrained. All right, well that's applying normalization to our plane wave, our free particle solution, and that concludes this example, this application. The next application will be a particle in a box, as I often have heard it called, as it's often called, or the infinite potential well.